Now we will assume that before these virtual displacements, the system is in a state that we will call state 1. And then the system, after these virtual displacements, will go to a state called state 2. And it will be another stationary state. Between the two states, there is a time interval which separates them, and it's delta t, what I call delta t earlier. Okay, so we can also call the kinetic energy at state 2, we will call it T bar 2 because it will be some kind of average, and I will show you how to calculate the average of the kinetic energy by using the distribution, Maxwell distribution. But before state 2, we have state 1, before this transition, and I will call the kinetic energy, the average kinetic energy, T1. So we can also rewrite this equation in this way. We have T2 minus T1, T bar 2 minus T bar 1, minus, and we have something similar for the potential. We have V bar 2 minus V bar 1 equal to delta Q. I will still rewrite it like that. And what about T bar? How can we calculate in general T bar? And after we calculate T bar, we will calculate it at state 2 and then at state 1. We have to consider this subtraction. Now let's calculate T bar. For T bar, we have to average over our distribution the kinetic energy. We wrote the kinetic energy earlier. It's 1/2 AIK, which is a function of the Q's, Q dot I, Q dot K. So we have to sum over I and K here. And then we have the Maxwell's distribution, which is e to the minus. Here we have the energy, which is given by the sum between the potential energy and the kinetic energy. So we have 1/2 Aij Q dot I, Q dot J, or maybe I can also use the same indices. It doesn't matter. In this case, I should call them in a different manner, but whatever. So I can still call them in the same way. AIK, Q dot I, Q dot K plus V. And then we divide by the Boltzmann constant, KB, times the temperature. For the temperature, I will still use the letter T, so please do not get confused between this T here and the T for the kinetic energy. For the kinetic energy, I'm going to write this T here with this notation, so I'm using this portion of the T is different, so pay attention to that, whereas for the temperature, I'm using this T with just 2 bars. For the kinetic energy, we have more than 2 bars. We have this bar, this straight bar, then we have this horizontal bar, and these 2 bars, which are still vertical. It helps us discern between these two T's. And then we have to multiply by dq1 dot 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 dqn, but we also have dq dot 1 dot 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 dq dot n. And we have to divide by the same integral of the distribution. In general, the distribution might not be normalized, so we have to integrate e to the minus 1/2 aik q dot I, q dot k plus V divided by K Boltzmann temperature dq1 dot 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 dqn dq dot 1 dot 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 dq dot n, like this. Now this calculation will be simpler if we go from the coordinates q1, qn, q dot 1, q dot n to the coordinates x1, xn, x dot 1, x dot n, because the kinetic energy will have a simpler form. So we will have integral of 1/2 mj x dot j squared e to the minus 1/2 we have mj x dot j squared. So in this case, remember, I could also call this index in a different manner because we have to sum this one separately from this one. Here we have to sum over j, and separately here we have to sum over j, but maybe I could have put k for these two indices, this one and this one, but I don't want to overcomplicate notation. We also have to sum the kinetic energy to the potential and then divide by K Boltzmann T. And then in principle here we also have the Jacobian of the transformation, but we know that this is equal to 1 for a canonical transformation. These transformations must be canonical. Then we have dx1 dot 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 dxn, dx dot 1 dot 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 dx dot n. Then we divide similarly by the integral of e to the minus 1/2 mj x dot j squared plus v divided by k Boltzmann t dx1 dot 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 dxn dx dot 1 dx dot 2 dot 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 dx dot n. Now in this case the integration over x1 xn will be very simple because it will be independent of the integration over x dot 1 and x dot n. So over x1 xn we only have to integrate the potential energy. So you can easily see that this ratio can also be written in this form. It's just the integral of 1/2 mj x dot j squared e to the minus 1/2 mj x dot j squared, and I don't have to put the potential anymore because it will get simplified by the denominator. Here we have k Boltzmann t dx dot 1 dot 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 dx dot n, and we divide by integral of e to the minus 1/2 mj x dot j squared over k Boltzmann t dx dot 1 dot 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 dx dot n. And also we can simplify this integration because in this case we have to sum over j here and over j here. But if you think about it, we have a sum of n integrals which are all the same. So we sum over n integrals because we are summing here. So when we sum over there, we are going to sum over 1/2 m1 x dot 1 squared, and that will multiply this exponential. Then we have plus the same integral of 1/2 m2 x dot 2 squared multiplied by this same exponential, and so on. Okay, so it's quite easy. But you can see that those integrals will give rise to the same result. So we will have n times the integral from minus infinity to plus infinity of 1/2 the mass of the particle. We're going to assume that the particles have the same mass, so that's important. m1 is equal to m2 is equal to m3. They're all equal, and we are going to put this constant equal to m. And then we have the velocity of one of the particles, the jth component. I'm just going to call it x dot squared in order to, let's say, make the notation easier. And here we will have e to the minus 1/2 m x dot squared over k Boltzmann t, and here we just have dx dot. So you can actually easily understand that all these integrals will become independent. You can easily see that there are some simplifications here when we take this ratio. Then here we'll have the integral from minus infinity to plus infinity of e to the minus 1/2 m x dot squared over k Boltzmann t dx dot, just like that. We can rewrite this integral in this fashion. This is equal to minus, and I will show you why there's a minus, and then we take the derivative with respect to 1 over k Boltzmann t of the natural log of integral from minus infinity to plus infinity e to the minus 1/2 m x dot squared over k Boltzmann t dx dot, like that. And we can call 1 over k Boltzmann t just beta, and this will simplify our notation. So here we will have m beta x dot squared. It's quite easy to carry out this integration because this is a Gaussian integral, and the result of this integral will just be the square root of 2 pi times the variance. Inside this square root, we have to put the variance of the distribution, the Gaussian distribution, which is simply equal to k Boltzmann t divided by m. So we have k Boltzmann t over m, or if you want to use beta, k Boltzmann t is beta to the minus 1. So this is equal to 2 pi over m beta to the minus 1 half. And now we simply have to take the derivative with respect to beta of the natural log of this. We are going to get, now let me also tell you that this minus is simply due to the fact that if you take the derivative of this expression, you will get back this expression here, of course. Now, this is a simple exercise. You just have to take the derivative. You have n square root of 2 pi over m. We have 1 half beta to the minus 3 halves. Let me write it properly. 3 halves. And then you have 1 over square root of 2 pi over m beta to the minus 1 half. And this is simply equal to n over 2 beta, which is equal to n over 2 k Boltzmann t. Right. T here is not the kinetic energy, but it is the temperature. Remember the difference between T and T written like this, okay? Now, therefore, when we take the average of the kinetic energy in a certain state, we have n over 2 k Boltzmann t. We need to find t bar 2 minus t bar 1. We are in two different states. The difference between these two states is given by the temperature, because n is a constant and k Boltzmann is a constant. Of course, also this factor is a constant. So we have n over 2 k Boltzmann T2 minus T1. This is what we want to use. And T2 minus T1 here, we can also rewrite it as a small change in the temperature like this. Because remember that the difference between the two states is given by a small time interval delta t. So we will also have a small change in the temperature delta t, like that. Delta capital T, call it whatever you want. And now we want to find something similar for the potential energy. That's what we are going to do next.